Hello, my name is Mang Ning, a master student from KTH. The work I'm going to talk about is YOLOv4-object, an efficient model and method for object discovery. The joint authors are Yao Lu, Wenyan Hou, and Mihai Matskin. Object discovery refers to recognizing all unknown objects in images, which is crucial for robotic systems to explore the unseen environments. People in the past segmented 3D images and identified the object by measuring the shape and recurrence across space. Ekkrons et al. Claims that objects can be discovered and segmented while change detection between two sets of 3D images in a time window. Hobart et al. Make use of video sequence to generate candidate regions and track them over time to pick out objects. Nevertheless, these object discovery methods don't apply to a single RGB image and don't perform well in a wide scenario. Recently, object detection models based on deep learning methods have shown remarkable achievements in object classification and localization. However, the category of detected objects must be explicitly predefined in models, resulting in a limited number of objects that can be recognized. For example, the screen and book in this image are not detected by the model. In this paper, we employ an object detector to realize robust and real-time object discovery in 2D images. Our method is based on object detection model, and it has two steps. First, we take YOLOv4 as the base model and set the number of category as 1 in the output space. Second, the label of all datasets is modified at the class object. For example, the monitor, keyboard, and mouse are all labeled as objects. The rationale behind our method is that we interpret object discovery as the essence of globally distinguishing meaningful foreground from non-meaningful background. Generally, the classifier of a neural network nonlinearly maps the feature space F into the object category space C by learning the classification function G. We propose to set the class amount C as 1. Thereby, the model will learn a decision boundary between foreground objects and background. Also, with all objects now regarded as the same class, the solution range of theta can be a set of the linear combination of original solutions theta1, theta2, or theta c. So, the solution range of theta now is wider than previously, and the network should achieve a better performance compared with its base model. We use COCO dataset in our experiments, and it has two properties that we want to point out. Only 80 categories of objects are labeled in COCO, and the distribution of class labels is highly biased. This figure shows that the category person dominates the whole dataset, and the remaining classes are also unbalanced. This property brings two problems for discovering all objects using our method. First, only a part of objects in images are labeled, which is against the learning process of all objects. Second, COCO would induce models to learn more features of person, reducing the proportions of other objects' features. Accordingly, we designed experiments to illustrate and alleviate those influences. Taking YOLOv4 as the base model, we first designed YOLOv4-object to implement object discovery with the output space set as object. In the meantime, we introduced the YOLOv4 human model to only recognize humans to show the performance of a normal object detector with one class. Then, the two models YOLOv4-human-object and YOLOv4-object fine-tune are constructed to illustrate the inference of COCO datasets. Concretely, YOLOv4-human-object detects two classes and aims at removing the dominant class human from the rest of all classes. In this case, the unbalanced distribution of training samples is greatly alleviated. In response to the problem of incomplete labels in COCO datasets, the fine-tuned model is designed and trained with 480 images that have been completely labeled. Finally, we proposed the slim version of YOLOv4-object by pruning the channels of some convolutional layers near the output layer. The experimental results are shown in the table. First, the recall and MAP of YOLOv4-object are higher than its base model. This result demonstrates that our model can detect more objects than its meta-model, and doing 80 classes object discovery in COCO datasets is feasible. Furthermore, the contrast between YOLOv4-object and YOLOv4-human indicates that detecting one specific category is easier than detecting generic objects, even though both of them are encoded as one class in the output space. We argue that it's challenging for CNN to learn the feature representation of the generic object class. Then, we analyze the output of YOLOv4-human-object from two focus points. First, its MAP is higher than YOLOv4-objects, verifying the inference of the biased training samples. Once the issue of unbalanced sample is solved, the model can better generalize its competence of object discovery. Second, the performance of YOLOv4-human-object suggests the extendability of our proposed method. It can be inferred that, using our method to detect the triplets human, interactive object, non-interactive object is also feasible. The results of the slim model suggest that our method for object discovery is compressible without loss of accuracy and recall. Finally, the inference of the incomplete labels in COCO dataset was verified via the fine-tuned model from two findings. The recall of the fine-tuned model rose from 65% to 67%, showing a better object discovery performance. We point out that a higher recall can be achieved by our method if the dataset is fully labeled. There are some demos for the comparison between object detection and object discovery by using our method. It's clear that our model can discover more objects than vanilla YOLOv4. This is consistent with the experimental results, where our model achieves a higher recall. The same results are shown in video detections. These are YouTube videos, and many detected categories are actually not trained in our model. In this paper, we explored the approach of using object detection models to discover all objects in images without explicit class definition. With the comparison of a set of experiments, we also show that the proposed method is transferable extensible, and compressible. Regarding the applications, we recommend two ways of using our method in practice. First, a generic detector can be trained by our method with complete labels. Second, the well-trained generic detector can be further concatenated with a category classification layer to do normal object detection. The advantage of the generic detector is that it implies a stronger proposal generator, which is similar to region proposal network of faster RCNN, but it is more accurate and powerful by using our method. As for the future work, we will further research the possibility of using our generic detector in transfer learning with much less training data. That's all about our work. If you are interested in it, don't hesitate to check out our paper and GitHub repository. Thanks.